Hello, I'm SeungWon Seo from the IIIXL Lab. Today I will be presenting a paper titled Agent Play Dozens of 3D Video Games. This paper is an archive preprint and focus more on presenting an interesting idea than on rigorous experimental validation. I choose it because it introduces a novel perspective on how LLM can be used in game AI, which I believe is worth discussing. Before getting into the method itself, let me first explain why this problem matters. Games have long been one of the most important testbeds for artificial intelligence. From classic board games to real-time strategy games, they have allowed us to evaluate planning, reasoning, and learning in controlled yet complex environments. However, the gaming landscape has changed fundamentally in recent years. We are no longer dealing with a small number of well-defined games. Instead, with the rise of user-generated content platform, we now have dozens of 3D games, each with different mechanic, rule, map, and objective. This shift creates a serious scalability problem for traditional game AI. Reinforcement learning approaches are powerful, but they are extremely expensive and typically tailored to a single game. Rule-based systems such as handcrafted behavior tree are efficient but brittle. They break easily when the environment changes. As a result, existing game AI techniques struggle to scale to this new setting. They work well for one game, but not for dozens of games. This leads to the key question that motivates this paper. How can we design game AI agents that generalize across dozens of different games rather than mastering just one? Now let's briefly look at why existing game AI approach fail to scale using this comparison table. Reinforcement learning achieves strong real-time performance after training, but it requires massive data and computation and is usually specialized to a single game. As a result, when the rule or map change, retraining is often necessary, making cross-game generation difficult. LLM-based approach offer interpretable decision and are relatively easy to deploy, but most of them rely on online inference at every step, which introduce latency and make them unsuitable for real-time games. In addition, difference in action space and interface across game make practical generation challenging. In short, both approaches are tightly coupled to individual environments, which limit their ability to scale to thousands of games. This limitation is the key motivation behind the perspective proposed in this paper. So far, we have seen that existing approaches struggle not because they are weak, but because they tightly couple decision making to real-time execution. This paper proposed a fundamentally different perspective. Instead of asking large language models to act in the environment, we ask them to design policy. In other words, language models are no longer treated as player or controller. They are treated as policy architect. The key idea is to shift the role of the LLM from online decision making to offline policy generation. The LLM reasons about strategy, structure, and high-level behavior and produce a policy representation that can be executed efficiently by the game engine. This separation of concern is crucial. Strategic reasoning, which benefits from the expressive power of language model, is performed offline without any real-time constraint. Execution, on the other hand, is handled by lightweight systems such as rule-based logic and small neural network, ensuring that the agent can operate under strict real-time requirements. This approach is called PORTAL, short for Policy Optimization and Reasoning for Tactical Artificial Learning. By reframing the problem in this way, Portal avoids the latency issue of LLM-based game playing while retaining the generation and reasoning strengths of language model. Now that I have introduced the core idea of Portal, let me explain how policies are represented in this framework. In Portal, a policy is defined as a triple. A policy pi consists of capital Pi, theta, and pi. Here, capital Pi represents the policy structure. It defines the hierarchical organization of decision making and is implemented as a behavior tree. This structure specifies when and under what condition different actions should be considered. The second component, theta, consists of neural network parameterized task nodes. These nodes are responsible for adaptive execution, such as navigation, aiming, or movement in dynamic environment. Importantly, these networks are intentionally kept small and lightweight. The third component, pi, contains rule-based node, including conditions check and simple deterministic action. These nodes provide precise and interpretable control over the agent behavior. The key design principle here is the separation between structure and execution. The high-level structure capital Pi captures strategic reasoning and decision flow, while theta and pi handle the actual execution of actions. This separation allows each component to be optimized independently. Most importantly, it enables the language model to focus exclusively on generating and modifying the policy structure without being burned by low-level control detail. Now that we have defined the policy representation, the next question is how a language model can actually generate such a structure. The key motivation here is that large language models need a structure and executable representation. Asking an LLM to directly output low-level action is neither reliable nor scalable. To address this, the author introduced a domain-specific language specifically designed for policy generation. This DSL has three important properties. First, it is human-readable. Designers can easily inspect, understand, and modify the generated policy. Second, it is machine executable. The DSL can be directly compiled into a behavior tree that runs efficiently inside the game engine. Third, it is hierarchical and its structure directly mirrors that of behavior tree. Indentation represents parent-child representation, making the control flow explicit. On the right, you can see a simple example of this DSL. At a high level, the policies say, if an enemy is visible, select one and shoot. Otherwise, move toward a known enemy location. Despite its simplicity, this example already encoded a complete decision-making strategy. Most importantly, the DSL serves as the clean interface between language model and game engine. Language model generate policy in this structure from offline, and the resulting behavior tree can be executed in real time without any online LLM inference. Let's now take a closer look at the syntax of the DSL and how it maps directly to behavior tree semantic. The most important design choice is that DSL follow a strict hierarchical structure. Indentation is not just for readability, it explicitly defines the parent-child relationship between nodes. As a result, the textual structure of the DSL corresponds one-to-one with the structure of a behavior tree. The DSL supports four primary node types. First, selector node implement prioritized decision-making. A selector evaluates each child in order and execute the first one that succeeds. Second, sequence node represent order execution. All child node must succeed for the sequence to succeed, which is useful for multi-step behavior. Third, condition node evaluate prediction over the environment state. They determine whether a certain branch of the tree should be executed. Fourth, task node corresponds to concrete action in the game environment, such as moving, shooting, or interacting with objects. The DSL also includes simple logical operation. For example, the condition no keyword allows negation, enabling the construction of more complex decision logic without introducing additional syntax. The key takeaway is that this DSL is not an abstract programming language. It is essentially a textual representation of a behavior tree designed so that language model can generate it reliably and game engine can execute it efficiently. This slide illustrates the hybrid architecture at the core of Portal. Let me first briefly recall how traditional behavior trees work. Classical behavior trees are fully rule-based and deterministic. They provide clear and interpretable control logic, but they struggle in dynamic environments with moving target, noisy observation, or complex interaction. Portal extends this classical framework by introducing neural network parameterized task node. Importantly, this node not mean that the entire policy is run. Instead, running is localized to specific task node where adaptability is most valuable. This leads to a clear separation of rule. High-level logic and decision flow are handled by the behavior tree, which remains symbolic and interpretable. Low-level control such as navigation or action execution is handled by a neural network that can adapt to environmental complexity. A crucial design choice here is that these neural networks are intentionally small and task-specific. They typically consist of only a few convolution and fully connected layers, and are trained with simple, focused reward objective. By avoiding large end-to-end model and complex reward function, this hybrid design achieves both stability and efficiency, which, while still benefiting from learned execution. As a result, Portal combines the strengths of symbolic reasoning and neural learning, enabling policies that are interpretable, adaptable, and suitable for real-time deployment. So far, we have seen how Portal represent and execute policy. The next question is, how are these policy structure actually generated and improved? The key idea here is to recast decision-making as a language modeling problem. Instead of learning a policy through direct interaction with the environment, Portal uses a language model to generate policy description expressed in the DSL. In this formulation, the language model does not output action, it outputs policy structure. Each output corresponds to a complete behavior tree that can be executed in the game. To explore the policy space, the system performs a structure search using a breadth-first strategy. At each iteration, the language model samples multiple policy candidates. These candidates are evaluated in the environment, and only the top-performing policies are retained for further refinement. This process allows the system to rapidly explore diverse strategies without requiring expensive policies retaining. Importantly, the data collected during this process is not traditional state action trajectory. Instead, it consists of language model trajectory, prompt-generated DSL policy, and their associated reward. This reformulation enables fast iteration, efficient exploration of the policy space, and a clean separation between strategic reasoning and execution. As we saw earlier, Portal generates policy structure using a language model. However, generation alone is not enough. The system needs a way to evaluate and refine this policy over time. This is exactly the role of the reflection module. Reflection forms a closed loop between policy execution and policy generation, ensuring that improvement is driven by feedback from the environment. The refinement process is iterative. A behavior tree is generated in DSL, executed in the game environment, and then evaluated based on its performance. Importantly, Portal uses two completely complementary types of feedback. The first is quantitative game metric. This includes objective numerical signals such as kill, death, objective completion, or resource uses. They provide precise feedback on tactical execution. The second type is vision language model analysis. Here, the system summarizes gameplay using a minimap style representation and asks a vision language model to analyze high-level behavior. This analysis captures strategic patterns, such as positioning, map control, and coordination, which are difficult to express using scalar reward alone. Reflection converts both forms of feedback into structured natural language and feeds it back to the language model. The language model then uses this information to revise and improve the policy structure in the next iteration. The key goal of this design is to improve both tactical execution and strategic behavior by combining numerical feedback with semantic high-level analysis. Portal achieves a more balanced and effective policy improvement process. We have seen the reflection improve policy using feedback. The next question is, what kind of feedback actually help improve high-level behavior? A key limitation of scalar reward is that they often fail to capture tactical quality. For example, an agent might achieve high accuracy but still position itself poorly or coordinate badly with teammates. To address this, Portal introduced VLM-based feedback. Since the environment does not provide a native minimap, the system syntactically generates one using map layout, player position, and status information accumulated over gameplay. This replay style representation are then analyzed by a vision language model. For FPS game, the analysis focuses on 5 dimensions: map control, adaptability, team coordination, team aggression, and goal achievement. This provides structured semantic feedback about tactical behavior, which complementary numerical game metric and help guide more meaningful policy refinement. We have seen how portals generate and refine policies through hierarchical reasoning and reflection. Now, I will explain how this process enables systematically policy exploration. The key conceptual shift is that portals reformulate decision-making as a language modeling problem. Instead of collecting state action trajectory from the environment, it explored the space of policy structure. Concretely, the language model generates multiple candidate behavior tree in parallel. Each candidate represents a different high-level strategy expressed in the DSL. These policies candidates are executed in the environment and evaluated using scalar rewards such as time between kill or objective completion. Exploration follows a BFS or the policy space. At each iteration, multiple policies are sampled and evaluated, and only the top K candidates are retained for the next refinement step. Although this process may resemble reinforcement learning, the unit of exploration is fundamentally different. Reinforcement learning explores state action pair, whereas Portal explores structured executable policy. At this point, Portal may appear similar to recent tool use or function calling approach. Its neural task node can even be interpreted as tool. However, the difference is fundamentally not superficial. In tool use paradigm, the language model stays in the execution loop, observe the environment, and decide which tool to call. This inevitably introduces latency, making such approach unsuitable for real-time application. Portal take a different approach. Here, the language model is not an actor but an architect. All reasoning and policy design happen offline, and the generated behavior tree is executed directly by the game engine without any LLM involvement. As a result, there is no runtime LLM inference and no latency bottleneck, while still benefiting from the strategic reasoning capability of language model. So far, I have focused on the methodology and conceptual contribution of Portal. Now, I would like to briefly discuss the experimental result and address a simple question: does this approach work at scale? The experiments were conducted on Youngman Star, a large-scale user-generated content platform developed by Tencent. This platform hosts a massive number of user-created games across diverse genres. In this work, the author focused specifically on thousands of 3D first-person shooter games. A key challenge in this setting is that this game differs substantially in visual style, map structure, mechanic, and level design. Despite this diversity, Portal applies a single unified framework across all environments, without per game retraining of language model or game-specific engineering. Empirically, the result indicates meaningful cross-game generalization. The agent exhibits consistent behavior patterns such as combat engagement, navigation, and interaction with the environment across different games. Through iterative refinement, the generated policy also show relatively stable performance over multiple generations. Qualitatively, the author reports behaviors such as coordinated combat, adaptive movement, and strategy transfer across visually distinct environments. These findings suggest that operating at the level of policy structure rather than lower-level action learning can provide a promising direction for a scalable game AI system. In the final slide, I will summarize the key takeaway and discuss the broader implication of the approach. Let me conclude by summarizing the key takeaway of this work and its broader implication. The central contribution of this paper is a shift in perspective. Large language models are not used as controllers that directly act in the environment. Instead, they are used as policy architects that design decision-making policy. By reformulating decision-making as language modeling problem, Portal shift learning and reasoning from the level of individual action to the level of policy structure. This perspective suggests that higher-level decision structure may generalize more effectively across environments than low-level action policy. From a practical standpoint, this design offers several advantages. First, there is no online LLM inference during gameplay, which makes the approach compatible with real-time constraints. Second, policy can be generated and updated without retraining large neural model or modifying game code. This makes the framework particularly suitable for UGC platform, where new games are continuously created. More broadly, the idea in this paper may extend beyond game. Domain involving hierarchical decision making such as robotic, embodied AI, and complex control system could potentially benefit from a similar separation between high-level reasoning and low-level execution. To summarize, Portal present a promising direction for using language model to design policies that are structured, interpretable, and compatible with real-time system. Thank you for your attention.